Okay, so this is a very simple and short section. However, it's very theory heavy. We just lots of proofs of different types of theorems, um, illustrating when it comes to now the determinant of a matrix itself, and how operations can be dealing with this matrix or alternative ways to find the determinants of different type of variations of matrices we've gone by, so like inverses and also the transpose it. So pretty much, again, very theory heavy when it comes to this section. So first theorem is let A be an n by a matrix. Then the determinant of A is the same as the determinant of the transpose, which is actually a pretty fun one to know. Second one is cut odd. Let A be an n by n matrix. Okay, so let B be a matrix that is formed by interchanging any two rows or columns of A. Right. So, for example, so now this is matrix A. So matrix B is some form of it where I just interchange any two rows. So there's only two rows, but kind of like that. And if that's the case, then the determinant of B is equal to the negative of the determinant of A. Very interesting one there, right? Going to respond to it. And because of this situation, we have this corollary is if A is an n by n matrix with two identical rows or columns, then the determinant actually equals 0. And that's actually a good one to actually know by heart or just going forward when it comes to the determinants of matrices and how to find them, or when we actually need to find the determinant of it for other purposes, like for the eigenvalues and all that. But so, like I said, very theory heavy. So we're going to prove this theorem and its corollary respectively. Okay. All right, so like everything else, we need to set up what we have. So just giving the situation, so suppose we have an n by n matrix A and matrix B. All right, and we'll just do the, which one should we do? We'll just do the row one. The column one's pretty much identically the same. Okay. All right, so we have that situation, right, what the theorem says. So now we got to figure out this, inner stuff. How in the world does this actually make sense? So we're going to go through, not entry by entry-ish, but actually row by row. Okay, so we're going to suppose the ith and the ith plus 1 ith row are the ones we interchange in A to make B, right? Well, I'll just go from there. Suppose the ith and I plus 1 row in A, so like specifically what it is. Oh, actually, in A form B. Okay, we'll start with that, the basic there. Okay, all right, now we'll get into the nitty-gritty stuff. Okay, all right, so now we're going to talk about the minor matrices. So the minor matrix of Jij, so we have this minor matrix Ij that's a minor matrix in row in A, when it comes with the ith row in A, and we're also going to say, I guess, yeah, we'll say the n I plus 1 is a minor matrix of the I plus 1 row. So this is the matrix of the ith component in A, and this is the minor matrix of the ith component row in B. Okay. All right. A little confusing where all the letters are, right? Okay. Now we got that down. So the cofactor expansion of the ith plus 1 row is, well, that means it's the determinant. So we'll talk about the determinant since we're having I plus 1. So that's the determinant of B broken down into its component format, right? So talked about last section corresponding to it is equal to the sum of all of this. So that's the, right, if it's positive or negative. And then we go into the actual entry of the actual matrix times the determinant of this minor matrix of the, or this minor matrix more precisely, of the j plus 1 itself. So this comes from the definition of what is a cofactor expansion, right? Now, it gets confusing because it's I plus 1, so that's why there's not just j just plus I, it's I plus 1 corresponds here, and same thing applies here. Okay, so simplify this a little bit because we can actually simplify this, believe it or not. We can take this 1 on the outside because there's just going to be 1, so we just pop it here. Again, just make things a little nicer to see, right? Okay. Oh, and actually messed up here. What am I talking about? This is the matrix I plus 1, comma j. There we go. That's the what I'm looking for. All right, so bringing this here now. This sum is pretty much the same, just kind of make it look a little nicer to look at. That way it kind of looks like the actual definition. So we take out that plus 1 here and just pop it in the front. Okay. Now, the reason why we pop this in the front is because, remember, we actually need a negative, right? So now what we're going to do is just bring it to the front. Okay. Now, this is where we go back to our setup here. Okay. Let's talk about this stuff right here. Okay. So we said that this is the minor matrix of the I plus 1 row of B, right? That's the one we just swapped around. And this one was the minor matrix of A in the ith row. Okay? But because we just interchanged these rows itself, okay, well, we know that the minor row or minor matrix of this one is the same as that one. This is in B and this is in A. Well, if that's the case, I could just swap them. And since this right here is the definition of a cofactor expansion of A, well, this just means this is the actual determinant of just A itself, or with a negative on the outside. And there we go. So very, very theory heavy when it comes to this section. Again, just proving lots of weird theorems going about doing so. I thought it would be a nice, interesting one, how this will break down just by knowing that interesting spec. Most of it, the work is literally somehow the setup of it, of how to do so. Okay, but the nice thing is the corollary is actually much easier to prove. It's much faster because it's a consequence of this actual theorem. So the corollary says if A is an n by n matrix with two identical rows or columns, then the determinant of A is 0. Okay, so we could just, I think I have enough space right here. And we'll just do, we'll do the same thing. We'll do the rows. Okay. So we'll let A be an n by n matrix with two identical rows. We'll call those ith and jth rows. They're the same. Okay. Okay, so now we're going to use this theorem itself. So if we interchange them to get matrix B, so if I literally just swap places, so I now get matrix B. So okay. All right, so now by this theorem, I know the determinant of B is equal to 1, so negative 1 times the determinant of A. Just by knowing that fact, right? Because we just proved it. Okay. Well, here's the thing going back over here. Since A and B are the same matrix, right? And it would make sense. Like, again, we give an example. If this is 1, 1, 1, 1, and I swap the rows, 1, 1, 1, 1, I get the same thing back. So in other words, matrix A actually equals matrix B. Well, if they equal the same thing, so that means if I just put those here, so that means the determinant of, just swap this to be A equals minus the determinant of A. Well, how in the world does that make any sense? How can we be equal to each other, right? Well, if this is 5, this can't be 5. It has to be negative 5 to make it true, right? So really the only way this is possible is if the determinant of A equals 0, right? Besides that, this will be not possible to solve for. So therefore, that has to be true. So, like I said, some weird theorems, corollaries going forward, but this is actually a really good one to know because it saves a lot of work to do so. Okay. So, a couple more theorems, and we'll actually do an example of how this is actually useful, or how these theorems are actually applied in a useful format. Okay. So, two more down here. Suppose that B is obtained from an n by a matrix A by multiplying one row or column of A by a non-zero scalar of C and leaving the other rows unchanged. Then the determinant of B is equal to C times the determinant of A. Okay. So again, so I'm multiplying only one single row or column by something in A, and that gives me matrix B. It's the same thing, just multiplying the determinant of A by C itself. Pretty interesting, right? And we're actually going to be proving that one in a little bit. And the next theorem is let A be an n by a matrix. Suppose B is the matrix obtained from A by replacing the ith row of A by the ith row of A plus a constant multiple of kth row of A. where k and I not equal each other. Okay, this is very, very obscure. We're actually going to do an example how this is useful and what it means by that to find the determinant. So don't worry, this is kind of a very weird one. But in layman's terms, what they're trying to say here is you could actually do row reduction, and you'll see that in a little bit, right? Because this is pretty much what is a row reduction. You're replacing the ith one row by another row that's similar to A with a constant multiple. So you kind of think about it, right? That's scalar addition right there. Well, multiplication slash addition. So in other words, it's row reduction. So this is a nice one going forward. Okay. But again, like everything else, kind of have to prove some stuff. Right? So we're going to prove the first theorem here. Right? So a lot of setup we're going to have to this theorem. So suppose B is attained by an n by a matrix by a multiple portion. So let me write that down. Let's see. Okay. Okay. All right, so there's our setup. All right, so now let's get to the little bit of the background information before we actually get to the proof. So that row we're going to call the ith row. So that the ith row in A be multiplied by C. Okay. So now we're going to let the minor matrix Mij of B, of this matrix B, with its cofactor expansion. So notice cofactor expansion comes a lot when it comes to proving stuff now. Okay. All right, so again, just like the last definition, so the determinant of B with respect to this cofactor expansion is going to be the sum of j equaling 1 to n Oh, so almost forgot. The most important thing. All right, this multiple C. All right, so remember, this part is in here, right? This is a minor matrix of B. So this scalar is in this portion, and it's the ith component. So it's some component there, fixed there. So that's actually the C value right here. Okay? So that's a C value being multiplied by that particular row. Okay. Now, the best part is, well, because it's a constant, right, just like 5, I could bring it all the way to the outside. Okay. So, in fact, if you want, I could bring it here first and then out here, because it's nothing to do with the actual summation. Okay. Well, what does this mean? So, again, Well, again, let's go back. So this was a minor matrix of B, right? However, if I just take that value out, therefore this actually is a minor matrix of the original of A, meaning nothing's really changed, right? Nothing has changed. This is the definition of its cofactor at this particular minor matrix, right? What was so special about it is just this letter C. This C was in its individual one here, but we took it out. It's not there anymore. So by definition, this right here is the determinant of A. Look at that. That's exactly what we get. So, like I said, lots of theorems, a lot of proofs, conceptually how we actually done. So let me give an example or two how these theorems are actually pretty nice to do so. Okay. So we're going to do an example of how the last theorem helps us out. This one right here. Okay. So like I said, I talked about this as technically row reduction. So I'm going to row reduce it. So according to the theorem, I'm going to multiply one of these rows by a value. I'll multiply the first row by -2, or sorry, by 2. So if I do that, I get this. And now I'm going to replace one of these rows by the sum of them. Well, if I just do that, so I'll leave everything else itself, and I just add it to the third row, that gives me 0. So what am I saying? It's not negative, it's positive. 5 and 3. Okay. And now, well, what if I get the determinant of this? Well, if I just get the determinant of this is the same thing as just getting the minor matrix of 1, 1, right? Cancel, cancel, which is nice. Notice, well, this is going to be 1 times the matrix 3, 5, 2, 3. And, well, minus 2 times matrix 0, 0, 2, 3. And then plus 1 times 0, 0, 3, 5. Well, if I get this determinant, well, this is going to be 9. So 1 times 9 minus 10 minus, well, this ends up being 0. And so does that. Well, look at that. It actually goes away. So it actually makes the determinant much easier to do so, just knowing that theorem, because it ends up being just -1. Okay? So that is what the power of that theorem really says is, well, now all I have to do is just row reduce it as much as possible. And that's the same thing as finding the determinant of the entire thing if I literally have to do every single step by step. Meaning, if I find the determinant of this the old-fashioned way, I will get the same result. I'm just slowly manipulating because of that theorem. Right? So like I said, it's basically row reduction when it comes to it. And now you actually don't have to do such a crazy, abstract breaking down into a 3, then 2, then finally 1. Okay? So, for instance, we could do the same thing here. Right? All right, so what I'm going to do is I'm going to do a lot of stuff because it doesn't tell me I can do it once. I can do it multiple times. Just ith row, kth row, whatever extra rows I want to do it. So I'm just going to row reduce this as much as I possibly can. But I'm going to row reduce it at a particular point in time. Okay. So what I mean by that is first I'm going to get these to be 0, like I did here. Well, this was already 0, but I just did it one time and got zeros. Okay. So I just row reduce it just to cancel all these 3's out. And eventually I just get this. So now, if I want to find the determinant of this, and if I follow this pattern, we're just going to cancel because it'd be zeros, I just get 1 times this matrix here. Well, again, if you really want, you can now do a determinant of a 3 by 3, which is not too difficult to do. But why don't we just do the same process again? Meaning, let's row reduce this in such a way that, again, these are zeros, and this is now a 1 again. So if I do that one more time, and again, just slowly manipulate this, I get this matrix here. And now again, if I just do the determinant here, the zeros will cancel everything else like we proved it right here, literally just cancel away. So now I can find my determinant quite easily. And all I have to do is multiply the individual components, because now this will be 1 times 1 times the matrix 15, 3, negative 11, and negative 2, which is much easier now. I just crisscross applesauce. So 1 times this gives me negative 30 plus 33, because the negative negative cancel out, get positive. So it just gives me positive 3. So it makes finding the determinants so much easier doing it this way. So that's the reason why now you could just row reduce it as much as you possibly can. But again, you have to row reduce it in a certain manner where you just get a bunch of zeros first and then you break it down individually. So now it becomes a 3 by 3 and eventually down to a 2 by 2 in that format. And if you do everything correctly, technically you kind of want ones here because ones is easier, right, to do so. But if there's a 2 here, you got to be careful. All that fun stuff. Just be careful. Usually you just want ones in the front, make it easier. But technically, you could have every single number is perfectly fine there. And so like in the meaning, I can swap these around and move everything around. But again, I wanted to use this particular theorem, right? So if I swap these around, then I have to do the other thing, which is going to be the minus of it. So interesting theorems, how this works out, how it's useful going forward as well.